Okay, so I have spoken with Professor Mondal about the first theory class test. So as most of you were preferring Friday, so it will be the class test would be on next Friday during class hours. The syllabus would be whatever would be covered till tomorrow. Okay, so basically this chapter which we are doing, yeah, till here, and we will send out the detailed instructions. As I said yesterday, it will be a proctored exam. That means you will have to keep your videos on such that we can see. I mean, there will be exam rooms where TAs would be there, and you would need to keep your video on so that we can see you during the exam. And then you write in on using pen and paper, and then scan and upload the answer scripts. Okay. We will send out detailed instructions very soon. But essentially next Friday, and the syllabus is up to whatever will be covered tomorrow. Okay. So let us continue what we were discussing. We are discussing that critical section problem. So we studied a software solution called Peterson's solution, but we understand that theoretically it is fine. Theoretically, Peterson's solution is correct, but in practice, modern architectures allow out-of-turn execution of instructions, and there Peterson's solution is not guaranteed to be correct. So essentially, we need some hardware support. We need atomic instructions. So basically, there should be some instruction to acquire a lock, and that should be atomic. That means often for acquiring a lock, I mean, we might think, oh, just acquiring a lock is just one instruction, but actually it is not. A high-level instruction can actually be translated into several machine-level instructions, and that we have seen. And therefore, it is not guaranteed that those multiple instructions function atomically. Therefore, what is needed is hardware support so that acquiring a lock can actually be an atomic operation. So we checked one example like test and set. So this, I mean, there's a target Boolean variable. This function tries to set that to true and returns the returns the previous value. However, the important thing to notice, though we are writing this in a C like it seems three statements. Actually, there is just one machine instruction for this whole thing, right? And it is guaranteed that this machine instruction will function atomically. Right? And if there is such guarantee, then you can simply do this. So while test and set lock, while that is true, that means remember test and set will return the previous value of the lock. So if the previous value of the lock was already true or 1, that means you should not enter the critical section. You should wait. This process should wait. Once the test and set returns false, that means the lock was previously not set. Now this process has been able to set it. The test and set. Now this process can enter the critical section. Okay. Okay, Deep has a question. What if some instruction of the critical section is executed out of order before the lock is acquired? Okay, that is a very good question. I must say I'm not very sure of this answer, but I think the compiler or even the the compiler would know that those instructions like the system calls. So basically acquiring a lock would be a system call, as we will see soon. So instructions after those should not be brought before the acquiring the lock. Okay. So yeah, that's a good question, Deep, but I'm not exactly sure of the answer. But since acquiring locks are system calls, because ultimately a hardware level instruction has to be accessed, since these are system calls, I think these are special system calls, and the compiler would know that not to reorder the instructions after that. Okay. Fine. Okay. So yeah, so this is one example of test and set. This is not the only one. There is another similar function called compare and swap. So here also the original value of the past parameter is value, and that is returned finally, and the variable is okay. So there is a condition first. First, it is checked if the value is the same as expected. Okay. If it is, then the new value is set to value. Right? And what is returned is the previous value. So intuitively, what is expected is that the lock is not locked. So expected is 0. So if the lock is not locked, then lock it. That means set the lock to the new value and then return the previous value, which is not locked. Okay. So ideally, if the lock is not locked currently, if the lock is open, this function will set the lock to closed or locked and return the previous value, which would be not locked or open. Now again, we are writing this as a C kind of function, but understand that this will be a one single instruction. For example, in the MIPS architecture, we can have a machine instruction such as CAS, compare and swap. So essentially this whole thing, what is written, if R1 equal to M1000, then M1000 equal to R2, this whole thing happens atomically. Okay. And again, if you have such an instruction like compare and swap, then you can easily solve the critical section problem by this kind of a logic, that you will try to compare and swap. That means with lock 0, 1, that means you expect the previous value of lock to be 0 and you want to set it to 1. If this call succeeds and returns 0, that means the lock was previously open and this process has been able to lock it. This process has been able to set 1. If this compare and swap returns 0, okay, sorry. Yeah, if this compare and swap returns 0, then this process has been able to acquire the lock. But if compare and swap returns something non-zero, that means the lock was locked from before. So then it should wait. So when compare and swap returns 0, this process can enter the critical section, and after finishing the critical section, it sets lock equal to 0. Like the lock equal to 0 is an indication. Setting lock equal to 0 is an indication that this process is done with its critical section. So others should get the chance. Okay. So we have discussed multiple requirements. So remember, we have discussed multiple requirements for any solution to the critical section problem. Mutual exclusion is just one condition or one requirement. There are other requirements like progress and bounded waiting. Now, the solutions that we discussed, like the solutions that we discussed, like test and set, compare and swap, these definitely satisfy mutual exclusion, but may not satisfy bounded waiting. Remember, bounded waiting means something like how many times is one process which wants to enter the critical section stopped from doing so because some other process is in the critical section. So bounded waiting says that there should be a bound on the number of times that a process wants to enter the critical section but is stopped because some other process is in the critical section. Okay, this is not exact technically, what I said is technically not fully correct. Sure, if another process is in the critical section and spending a lot of time, then nothing can be done. And bounded waiting says that if no other process is in the critical section and one process has asked for entering the critical section, there should be a bound on the number of times that some other process is allowed to enter the critical section instead of this process. Right? So suppose the critical section, suppose the critical section is not. The critical section is no process is currently in the critical section, but sometimes many processes are wanting to enter the critical section. Then it should not be that a particular process, say P1, is made to wait many times because all other processes are being given the chance to enter the critical section, but not P1. That is the criteria of bounded waiting. However, what we have discussed till now, like test and set, compare and swap, these do not, these are not guaranteed to satisfy the condition of bounded waiting or progress. Mutual exclusion, yes, they will satisfy, not the others. So the next slide shows another algorithm using test and set that satisfies all the critical section requirements. So this is the function. This I am not going to explain in class, but you should look up the book, the Galvin book, to understand how this algorithm, which is shown here, satisfies all the critical section requirements. So as you see, just locking a lock is not enough. That is only enough for mutual exclusion. But some other ways like waiting, etc., other variables, other parameters are needed to ensure bounded waiting and progress. Okay, so this algorithm is well explained in the book, so do look it up. Okay. We are now going to start a new subtopic. Any questions about at this point? Okay, if not, let's move on. Okay, so till now we have discussed what race condition is and the critical section problem. And we have discussed some solutions to the critical section problem, namely the Peterson's algorithm, which is a software solution, and like hardware solutions, that means special atomic instructions, like test and set and compare and swap. Now, let us discuss other solutions like mutex locks. So this test and set and compare and swap, these are low-level instructions. Remember, we were writing them in a C function-like way, but actually they are low-level machine language statements. Therefore, these hardware-based solutions are not generally accessible directly to application programmers. Okay, so these are actually assembly-level, say, instructions or machine instructions, which the application programmers would not find easy to use. Hence, the operating system designers have built some software tools to solve the critical section problem. Right, so the simplest such tool is a mutex lock. So this is the lock. From the name, it's clear. It's a mutex lock, mutual exclusion lock, mutex lock. You have to first acquire it. A process has to first acquire a lock before entering the critical section. And after completing the critical section, it has to release the lock. So essentially, mutex lock is a Boolean variable indicating if the lock is available or not. However, the key point is that this is not any ordinary Boolean variable. The key point is that this acquire and release must be atomic. Okay, so underlying, if you go into the details, these are implemented via hardware atomic instructions. But again, we at a application programming level, we would not like to directly use the hardware atomic instructions. Therefore, the OS is giving us these tools like software tools. So this is how you would use locks. So first, see at the bottom of the slide, this is what you do standard. Before entering the critical section, you will acquire lock. And after completing your critical section, you will say release lock. Okay, but then how is the acquire lock and release lock implemented? That is what is shown here. So there is let's say a Boolean variable called available. So in this acquire function, while not available, go on waiting. So there is a semicolon here, right? So this is busy wait. This is called busy waiting. So as long as the Boolean variable available is is true, go on waiting. If it is false, that means if the value of available is true, then this process will set it to false. Okay, so as long as the value of available is false already, this while loop will execute. And once it, that if that is not true, that means available value is available value is true, then the available will be set to false. Right. And release simply sets available to true. Okay. Now this mechanism is called a busy wait. That means as long as some variable say does not have a desired value, wait, like just do while, just go on in an infinite while loop. So okay, not an infinite while loop, but basically, as long as the variable does not have a desired value, just go on pulling it, go on checking its value. Okay. A quick question here. This idea that as long as a variable value is not what I do want, go on executing a loop. Is this good from an efficiency point of view? It's correct, okay, but is this good from an efficiency point of view? Why, Deep? Why no? Just unmute yourself and say.
Sir, because like another process could have been scheduled on that CPU, but this process will simply hog the CPU as long as it does not, as long as available is true.
Right, very good answer. Yes, that's the thing. Yeah, Ashutosh also said the same thing. Ashutosh Nitsar. So this busy waiting has a disadvantage that CPU cycles are being wasted. Right, so it would have been better if some other process could have used the CPU cycles. Remember, CPU is a very expensive resource. We don't want CPU cycles to be wasted. Okay, so that's why this type of busy waiting is not very desirable, except in some special cases. So there is also an advantage that there is no context switch when a process must wait on a lock. Right. So as you understand, we will discuss the other alternative to busy waiting. That is what we have discussed earlier in the course also. That for some reason, if a process cannot proceed, then get it to the wait state and schedule some other process. But then this will require a context switch, right? So if it is the case that locks are expected to be held for very short time intervals, then maybe busy waiting is fine. Because the context switch also has an overhead, right? So if the locks are expected to be held for a very short interval of time, then maybe busy locks are fine. Because the alternative is to schedule some other process, which means a context switch, so there is overhead there also. However, still, because processes can spend a lot of time in the critical section, locks are usually held for quite long time. That means it is not uncommon for a lock to be held for quite a few seconds. That is why busy waiting is not preferred. We will see the other alternative soon. By the way, this kind of a busy waiting, this kind of a mutex lock, which we discussed, which uses busy wait, this kind of a mutex lock is also called a spin lock. Like the process spins while waiting for the lock to become available. But so in a special case where locks are held for a few very short amounts of time, it's fine. But usually, a busy waiting or spin lock is not advised. Okay. However, these mutex locks are there. For example, we have discussed that pthread library. Remember, when discussing threading, the pthread library has these functions. So essentially, there is a data type called pthread mutex t. Okay, so if you declare a variable of this type, that will be a mutex lock for use by your threads in the process. So you can initialize a mutex lock like this, pthread mutex t variable, and then you have these functions like mutex lock and mutex unlock, and finally you have mutex destroy. So again, I'm not going into details about these functions. You should look it up as and when necessary. Here is just one sample code of what you can do. So you declare a variable of this type, pthread mutex t. Okay, let's say this is the global variable. And then this is how you initialize the lock. Okay. And once you have the lock, then you can simply say this before entering the critical section. You can only say pthread mutex lock address of lock. Once the control passes through this statement, it means this thread has acquired the lock, and then it can enter the critical section. After the critical section, it will unlock. Right? And at the end, like when the lock is no longer required, you can use pthread mutex destroy. So again, not going into the details of these calls. You can find out from the man pages or internet and so. Okay, so that was about mutex locks. Simple solution to the critical section problem. Again, only, by the way, all these things that we are discussing, they help in the mutual exclusion condition, but they are not guaranteed to, satisfy the requirements of bounded waiting and progress. Keep that in mind. Okay, so mutex lock is one like software solution, but again, the difference of this with Peterson's algorithm is that Peterson's algorithm is completely algorithm or software dependent. However, the mutex locks and semaphores that we are going to study now, these are kind of software tools which you can use in a program, but underlying they use the hardware atomic instructions. Therefore, they do not suffer from the same problems as the Peterson's algorithm suffered from. Okay, so mutex locks we have discussed very basic, like just a Boolean variable. That means, yeah, I mean only mutual exclusion is guaranteed. However, semaphores are a better version of mutex locks, which will allow us to do many different kinds of things. So let's see. So yeah, it provides a more sophisticated ways than mutex locks for processors to synchronize their activities. Because see, just as a motivation, mutual exclusion may not be the only requirement. As mutual exclusion only says that okay, two processors should not enter the critical section. But you might have other kinds of requirements such that, for example, you might have other kinds of requirements. For example, you have two processors, process P1 and P2. You want some P2 to do something before P1 attempts something else. Okay, let's say P2 is the producer and P1 is the consumer. So first P2 should produce something and then P1 should try to consume. So basically you want different type of synchronization, not only say mutual exclusion, but also you want temporal synchronization among the processes. So actually you can have many different types of requirements for synchronizing processes or threads. So semaphores allow us to do those. So let's see. The first difference with a mutex lock is that a mutex lock was just a Boolean variable, but a semaphore is an integer variable. However, it's not any normal integer variable. It is a special integer variable which can be accessed by two atomic operations. Apart from initialization, yes, you can initialize the semaphore, and then you can only access it using two atomic operations. They are called wait and signal. For historical reasons, they are also called P and V. Okay, so wait is called P and signal is called V. Different books or different resources use different terminology. Some say wait and signal, some say P and V. But essentially P, I mean, when we say P, basically we are meaning wait and When we say V, we are meaning signal. Then we will define these PV things soon. Essentially, it's an integer variable which can be accessed using these operations only. I mean, you cannot multiply a semaphore or divide a semaphore. So don't think it of an integer in that way. Yes, internally it's an integer variable plus something else. We will come to it. It can be accessed only by these atomic operations. So what is weight? Weight is essentially what we discussed. I mean, analogous to what we discussed as lock in mutex locks. So while s less than equal to 0, weight is the weighting, and then s minus minus. So weight is essentially trying to reduce the value of s by 1. However, if s is already less than equal to 0, then it has to wait. Okay. And definition of the signal operation is simply s plus plus. Note that again we are writing these in a C-like function, but actually these are atomic. Okay. Now, essentially what is going on is, so s is this variable, integer variable, and it is, I mean, you can set it up as only binary, like 0 and 1. However, suppose you have a resource which has 5 instances. So you can allow 5 processes to simultaneously access that resource because there are 5 instances of the resource. In such cases, you can set the value of s to 5. So you see, the first 5 processes which tries to acquire the semaphore would not have to wait because s starts with 5, let's say. One process executes wait, the value of s becomes 4. Another process executes wait, the value of s becomes 3, and so on. So the first 5 processes don't have to wait. But if any other process, if any 6th or 7th process comes, then they would find s is already equal to or less than 0. Then they have to wait. Okay. Once s becomes positive, that means higher than 0, then s minus minus is done, and then the process has acquired the lock or has acquired the semaphore. Okay. So I hope that you are getting the idea that semaphore is more versatile than mutex lock. Mutex lock has just this Boolean variable, but because semaphore is actually an integer, you can control multiple instances of a resource by setting s to 5, 6 or something like that. You can again use semaphore as a binary mutex lock. Just set s to 1, so essentially 1 and 0. But semaphore is more versatile. It also gives you ability to do other things. We will discuss applications of semaphores. If it is not completely clear, don't worry, we will soon discuss. So yeah, so essentially there are 2 types of semaphores, a counting semaphore and a binary semaphore. So counting semaphore is an integer value that, I mean, we say it's a counting semaphore if the integer value can range over an unrestricted domain. If you see in the previous slide, s minus minus, s plus plus. So essentially, s is just being treated as an integer which can have a positive value, 0, negative value. That is a counting semaphore. And a binary semaphore is similar to a mutex lock. Essentially, the input value can range, and the integer value can range only between 0 and 1. How to use a semaphore, counting or binary, that depends on you. Whatever your application requires, you should use the semaphore like that. But semaphore is more versatile. It allows you to be used in a counting semaphore type of way. So in that way, it is more versatile than mutex lock. Okay, so now we will study some example uses of semaphores. We can actually solve different synchronization problems using semaphores. You will see 3 problems being discussed: mutual exclusion, process synchronization, and resource counting. First, let us talk about mutual exclusion. This is what we have been discussing since yesterday. So for mutual exclusion, assume that you will use simply a binary semaphore. By the way, again, don't think there are two types of semaphores, binary and count. Semaphore is just one type. You decide whether to use it as a binary semaphore or a counting semaphore. So use a binary semaphore S where value can be 0 or 1. Initialize S to 1. And every cooperating process has this structure. Before entering the critical section, process calls wait. And after completing the critical section, the process calls signal. Okay. So essentially, again, let me go back to the previous slide once. So if the value of S is 1, then a process will be able to acquire the semaphore, and then the value of S would become 0. This process can enter the critical section. Now the value of S is 0. So any other process which also calls wait on S should wait. It cannot enter the critical section. When this process which has entered the critical section does a signal, then it does S++, and then the value of S becomes 1 again, and then some other waiting process can acquire the semaphore. Okay, so that is how semaphore is being used for mutual exclusion. Wait S, when calling wait S, the process is trying to reduce the value of S. But if it is already 0, the value of S is already 0, then it cannot, it has to wait. Or it has to go on in the infinite loop. It cannot enter the critical section. Only when some other process does a signal S, then the value of S becomes 1. Then this process can enter the critical section. Okay. Any questions here? Okay, let me then proceed. Yeah, so this is about mutual exclusion. The next application is process synchronization. Right. So suppose we have this situation. I'm asking you a question here before going to the next slide. I guess many of you have understood it, but let's see. Suppose we have this situation that process 1, P1 has an instruction and P2 has some other. Okay, so suppose we want. Yeah, okay. Suppose P1 is a producer and P2 is a consumer. We want the producer first to produce something, then only the consumer should consume it. It's essentially we want P1 to do something before P2 can proceed. How do you think we can use a semaphore for this? We want P1 to do something before P2 can proceed. How do you think we can do this using a semaphore? Okay, Ravi, unmute yourself and say what you mean.
Sir, so we want the producer to run before the consumer. So if we set S to 1 in the producer, then whenever it sees the whenever it calls the wait function, then it will see only 1. So it will not wait.
When a semaphore is shared between two variables, so essentially we are talking about the semaphore shared between two processes. You cannot say the same semaphore will have value 1 in producer and 0 in consumer. Right? A semaphore has to have one initial value. A semaphore which is being used in this way, that means it is being shared between two processes, you cannot initialize it to different values in two different processes. Okay. Yes, I think Abhilash and Preet Kumar have given the correct answers. Okay, so good. Let's see the next slide. I think Abhishek and Abhilash and Preet Kumar yeah, gave the correct answers. So yeah. So suppose this process P1 has the statement S1 and P2, process P2 has the statement S2, and we require S1 to be executed before S2. Then create a semaphore, the cinch initialized to 0. P1 initially does not wait. It does S1 and then it signals cinch. Right? P2 before executing S2 waits on cinch. So see, cinch is initialized to 0. So P2, if it also reaches this statement or wait statement, it has to wait because as cinch is initialized to 0. P2 will be able to execute S2 only after P1 signals cinch. And by then P1 would have executed S1. Okay. Yeah. So good, yeah, good answer. Especially Preet Kumar explained it well. Yes. Okay, so again you see semaphores are quite versatile. That means they do not only allow you to do mutex, mutual exclusion, they also allow you to do this kind of temporal synchronization where you want something to be happening before something. So remember when we talked about parent child like fork statement, we then discussed that you cannot guarantee which will run first. So after a fork has happened, there are two processes. Now you cannot say which one will run first, parent or child. But if you want the child to run first than the parent, or the reverse, then you can use such techniques to ensure those things. Right? So essentially, if you want the child to do something before the parent gets to a point, then you can use this kind of uh, mechanisms. Okay. So semaphores are pretty versatile and useful. The third application that we are going to see is resource counting. Okay. So essentially, we want to keep track of a given resource which has a finite number of instances. So a simple way would be to use a counting semaphore. Okay. So initialize the counting semaphore to the number of instances of the resource that is available. Each process that wishes to use an instance of the resource performs wait, and when a process releases its instance of the resource, it does signal. Simple. Say you have 5 instances of the process, 5 instances of the resource. You initialize the semaphore to 5. So every time a process wants to acquire one instance of the resource, it has to do a wait. So since the semaphore is initialized to 5 processes will be able to wait without waiting. Okay, bad English. What I'm saying is, since the semaphore value is initialized to 5 processes will be successfully able to execute wait and acquire the semaphore because the semaphore value is 5. So 5 processes would be allowed. After wait has been executed 5 times, the value of semaphore would be 0. And then no other process would be allowed because there are only 5 instances. When one process releases its instance of the resource, it will signal. So again, the value of the semaphore would increase. Some other process can wait and so on. Okay. So a question is written at the end of the slide, which should be simple. Yes. Do you think this can be used to solve a problem we have discussed earlier in this course? So I guess it's easy. I mean, if you remember, so we discussed this producer-consumer problem with a bounded buffer. Okay, so that is one situation which can also be handled using such semaphores. So you somehow set the semaphore to the number of buffers, and then the producer, every time it wants to produce something, it has to, it does a wait, and so that way the producer should not try to put in more items than there are buffers, and therefore this kind of a counting semaphore can be used for that purpose. And if the consumer has consumed an item, that means that buffer has become empty again, then the consumer does a signal on the semaphore. Okay. This was the application of various applications of semaphores. However, we have not still solved one problem. If I go back to this slide, which defined wait and signal, we still see busy waiting. Right? So while s less than equal to 0, like just a semicolon here. So basically it's a go on looping as long as the value of s is less than equal to 0. This busy waiting we discussed, we do not, it's not efficient. So since applications may spend lots of time in the critical section, so busy waiting is not desirable. So what can be done? Till now we were telling just have consider a semaphore as an integer. Now we are going to add something more. Along with the integer, there will be a waiting queue. Okay. So if a process executes wait s, where s is the semaphore, and finds that s value is not positive, the process will block itself. Okay. And this process will be placed into a waiting queue for s. Remember, we had talked about process states. Essentially, this process, which was executing, is now going to a waiting state because it is waiting for the semaphore. And then the CPU can be scheduled to some other process because this process is waiting. Similarly, if a process executes signal s, then if any other process is waiting for that s, that should be moved from the waiting queue to the ready queue. Okay. So now how will wait and signal look like? I think the idea will become clear in a couple of slides. So wait. So with each semaphore, there is an associated waiting queue. So essentially now a semaphore has two ret items, a value of integer type and a queue. That means the starting pointer to a queue. And there are two operations apart from P and V. These operations are so the processors will still call P and V. However, there should be two associated operations, block and wake up. So block is place the process which has invoked the operation on the appropriate waiting queue. So a process executed wait s, the value of s was 0 already or less. So this process should be blocked. Okay, that means it should be placed in the queue of processes waiting for s. And another operation will be wake up. So if a process has signaled s, that means increases the value of s, then remove one of the processes in the waiting queue and place it in the ready queue. Okay, so let's see how wait and signal would now be implemented with these changes. So now the semaphore looks like this, a structure which has an integer value and a pointer to a starting queue. So basically struct process starting pointer to a queue. Okay, and this is what wait and signal would look like. So if you see, we have removed that while loop which was doing busy waiting. Rather, now wait does this, it tries to reduce the value of s by 1. Actually, not tries to, it reduces the value of s by 1. And then it checks if s value is less than 0, then this process is blocked. That means add this process to the s list. S list is the list of processes waiting for s, and block this process. Okay. And in case of signal, it increases the value of s by 1. And if the value of S is less than equal to 0, then it removes the process P from this list of processes waiting for S and then wakes it up. Okay. Fine. So now, couple of points here. See, S value minus minus directly is done. Is this okay, or should it have checked first that is the value of S less than 0, etc. Okay, think about it. If anyone has any question, then ask. So essentially, if you see how is the busy waiting removed here, and still okay, this is correct. This is not wrong, but just think about a bit that how is the busy waiting removed and still this works. So essentially, S value minus minus, this is actually not, this is fine because the value of S can go, so if say 5 processes are waiting on it, it might happen that the value of S is minus 5. It's possible. The idea is that all these processes are blocked. So after reducing, so suppose the value of S was already 0. Now this process does S value minus minus. So if the value of S is now less than 0, then this process will be blocked. Okay, so that is the key idea to understand how this busy waiting is done away with. Okay, so couple of points to mention here. So if you are wondering how the link of the processes waiting for the various semaphores can be implemented, then remember we have this PCB process control block which we have discussed. So we can easily have a link field in the PCB which will help to maintain this kind of a queue. That means the queue of processes waiting for a semaphore. Essentially, it has to be remembered. The kernel has to remember somewhere that which processes are waiting for this semaphore. So it can use the PCBs or some fields in the PCB for that purpose. Also, the wait and signal operations must execute atomically. Okay. So again, the wait and signal that we depend on, that the wait and signal will be atomic, and somewhere lower down, maybe a programmer will only call wait and signal, but somewhere lower down, atomic hardware instructions such as TAS and CAS will most probably be used. Okay. So semaphores are versatile, as we have seen, and they give good mechanisms of doing not only mutual exclusion but also different kinds of synchronization. However, even with all this, even semaphores cannot always guarantee progress. Let's see one example. So let's say we have two semaphores, S and Q, and the two processes P0 and P1. P1 calls wait S and then wait Q. And sorry, P0 calls this. And P1 initially calls wait Q and then wait S. Now it can happen that P0 executed first, it successfully called wait S, right? But then immediately after this, so it has acquired the semaphore S. P0 has acquired S. Immediately after this, there was a context switch. P1 started executing, and P1 called wait Q and successfully acquired Q. Now there is a problem because P1 is waiting. Now the next statement in P1 is to wait for S, which it cannot acquire because P0 has acquired it. So P1 will be blocked, P1 will wait. Problem is even P0 cannot proceed because the next statement in P0 is wait Q, which it cannot acquire because P1 has acquired it. So essentially, we will reach a situation where P0 is waiting for P1 to progress and P1 is waiting for P0 to progress. And neither of them would be able to progress. Okay. So essentially, they are waiting indefinitely for an event, which will never happen because that can only be caused by one of these waiting processes. This kind of a situation is called a deadlock. Okay. So if you see the kind of a bit of a formal definition, two or more processes are waiting indefinitely for an event that can be caused only by one of the waiting processes. In other words, that event will never occur because that event could have been caused only by one of the waiting processes. So all the processes which could have made that event to happen are waiting. Right, so this can lead to, so even with semaphores and all, if you are not careful about how you are using semaphores, it can lead to deadlock and starvation. Right, so starvation again means indefinite blocking. Let's say a process is never removed from the semaphore queue in which it is suspended. Okay. Okay. Yeah. Fine. So I think we will stop here today and continue tomorrow. Any questions at this point? Okay, do look up these things and yeah, I mean, think out a bit about how semaphores are avoiding that busy wait and yet functioning correctly. Okay then, thanks everyone. We'll continue tomorrow.